MS Ramaya University of Applied Sciences.
Universal Testing Machine is commonly known as UTM. It is used for testing mechanical behavior of materials. Mechanical properties of materials such as tensile strength, compressive strength, shear strength, etc. can be measured using this equipment. Other than the stress-strain diagram, different mechanical properties can be explored for a variety of materials, such as relationship between load, strain, and deflections in beams, tension members, other structural elements, and performance of structural connections. Tensile test using UTM. Tension test is the most commonly carried out test in UTM. This test provides information on the strength and ductility of materials under uniaxial tensile stress. This information may be useful in comparisons of materials, alloy development, quality control, and design under different conditions. The outcome of tension test is in the form of load versus displacement curve. The obtained load versus displacement curve is converted to a stress versus strain diagram. The generated stress-strain diagram can be used to calculate yield strength, Young's modulus, ultimate tensile strength, fracture strength, ductility, resilience, and fracture toughness. Sample size specification. The samples are prepared according to ASTM E8 standard.
Hi students, I am giving the details to carry out tensile test on universal testing machine UTM. For that I have taken two different materials, mild steel and aluminium, and these samples are prepared as per ASTM standard E8 for metallic materials. I am going to give the details of mild steel sample. These are gripper length and gripper area which gets seated in the UTM arms, and this is very important, which we treat it as the gauge length and the gauge dia, and we have to have the initial diameter and the initial gauge length that I am performing it. For that we have to mark 2 points which help us to have the initial gauge length, and then with the help of vernier I am measuring the initial gauge length. Which is 95.30 mm. Now I am measuring the diameter, 11.85 mm. Similarly, the procedure is adopted for aluminum sample also, where we take initial gauge length and initial diameter. We can have different gauge length, as you can see here, for mild steel and aluminum, and then after getting the initial data, then we have to carry out the test on UTM. This is a computerized servo hydraulic universal testing machine to carry out tests like tensile test, compression test, shear test, 3-point bending test. I'll tell the parts of the universal testing machine. Here you can see 3 crossheads: upper crosshead, middle crosshead, and lower crosshead. This upper crosshead and middle crosshead will help us to carry out tensile test, and this middle crosshead and bottom crosshead help us to carry out tests like 3-point bending, compression, and shear test, and this is operated by hydraulic pump. This is the control system which helps us to carry out the test on universal testing machine. The details are, this helps us to control the hydraulic pump so that the piston will operate to carry out the load. Hydraulic control valve, which makes the movement of the piston. This panel helps us to have the middle crosshead moving up and down, on and off. Load control valve while carrying out the test. The data is decoded and it is captured in the software. This is the middle crosshead, will move up and down to accommodate different sizes of the sample, plus to conduct tensile test and compression, bending and shear. I have taken the mild steel sample to carry out tensile test. These are the gripper areas. This will get fixed in the upper gripping area and this one in the middle gripping area. You can see that this gripping area will sit in the upper jaws. We have to ensure that gauge length is not disturbed. After it is held, it has to be securely tightened. Then the middle crosshead has to be moved up to ensure the gripper area gets fixed in the jaws. To fix the lower part of the sample, the middle crosshead has to be moved upwards to ensure the proper gripping with the jaws. Compression and bending, I have selected tensile test. Okay. Specimen round. Okay. Test data. Mild steel. Initial diameter 12 mm. Original gauge length 200 mm. It will calculate the area. Okay, and you can give other details to get the final output. Units kilonewton per mm square. Online scale, we can fix the range for x-axis and y-axis. Okay. Start test. It has calculated the area, initial diameter, and here we have fixed the scale for x-axis and y-axis. Now we have to tell online the data from the decoder is transferred onto the software. Before starting the test, we have to make zero load, zero displacement, and then say yes. It will go to the graph mode. This is the tested mild steel sample. We can see the necking and the fractured area. After it has fractured, we have to measure the final gauge length and the final dia at the neck portion. The fracture has got two regions, the cup region and the cone region. Call it as cup and cone. Similarly, the tensile test was carried out on aluminum sample also. We could see more cup region and cone region in the aluminum since it is more ductile than mild steel.
Let us understand more about stress-strain relation for a material using UTM. We take a steel bar as per ASTM standard and deform it using UTM. The stress-strain diagram of this bar is as seen in the plot. When load is applied continuously on the steel bar, the steel gets elongated. Thus, we get a plot of load versus displacement in UTM. This is then converted to stress, that is load by area of cross-section versus strain, that is change in length or original length. Thus, we get a stress versus strain curve for steel bar. When the steel bar is under continuous load, or in other words tensile stress, it elongates. In the beginning, we see that elongation is linearly proportional to applied stress. If the load is released, the steel bar goes back to its original length. The point here is known as proportional limit. Within this limit, where stress is proportional to elongation, it is said to be in elastic limit and it follows Hooke's law, which states that stress is proportional to strain. Now, as we increase the load onto the steel bar, it can be seen that stress is no longer proportional to the strain. It does not follow the Hooke's law. But as we release the stress, it goes back to its original length. The limit of this curve is known as yield point. The material's yield strength is given from this point. As the load increases further, strain also increases, but the curve no longer follows Hooke's law. In other words, it means that after releasing the stress beyond its yield point, the materials will not come back to its original length. This deformation is known as plastic deformation. As the load increases, the further stress reaches a maximum, at which sudden decrease in the cross-sectional area of the materials takes place. This is called as necking of the material. The point here is known as ultimate tensile strength of the material. As we further increase the load, stress required to strain the material goes on decreasing and finally the material breaks. The point here is known as breaking strength or fracture strength. Area under the stress-strain curve in the elastic limit is known as resilience, and the area under the whole stress-strain curve is known as the fracture toughness.
In general, the modulus of elasticity or Young's modulus of mild steel will be approximately around 210 GPa and Young's modulus value for aluminum will be around 80 GPa. Other than modulus of elasticity, the other important property, namely material stiffness, can be calculated using stress-strain curves. The following is the formula for calculating the material stiffness of any given material. Other material properties which can be interpreted from stress-strain curve is modulus of resilience. Modulus of resilience is nothing but the amount of energy absorbed by a material in the elastic region. Also, strain energy can be calculated using the stress-strain diagram within the elastic limit as shown in the shaded part of the stress-strain curve. The equation for calculating the strain energy from stress-strain curves is given below. Next important property which can be determined from stress-strain curve is toughness of a material. The toughness of a material is the amount of energy absorbed by a material up to the fracture point, which can be seen in the shaded portion of stress-strain diagram. We can see the stress-strain diagram of high carbon steel, medium carbon steel and low carbon steel. It can be clearly observed from the figure that As the percentage of carbon increases, the strength of steel increases, whereas ductility and toughness decreases. High carbon steel has the highest strength and low carbon steel is more ductile in nature. The reason for high strength in high carbon steel is due to more amount of cementite and pyrolytic phases of microstructure which can be seen in the image. Low carbon steel is more ductile in nature and has a ferritic phase of microstructure. Medium carbon steel has a mixture of both ferrite and pyrolyte phases and is the most toughest material when compared to low carbon steel and high carbon steel. This slide shows the FE simulation carried out in LS Dyna for tensile specimen. The figures show the displacement plots with various fringe levels. The stress strain curve and failure strain rate as observed in the simulation results matches that with the experimental tests.
At MSR UAS, we spark your imagination unlike any other.